All right, it is now the top of the hour, so let's get this party started. I see that we have a lot of MLCC fans out there, so that's great. I would like to welcome you to this now, our first webinar of 2021. I hope everybody had a good holiday break and Happy New Year to everyone. My name is Wilmer Compagnoni and I lead the technical marketing team at KEMET. And as usual, this webinar is one of the first of our series of webinars in 2021. And we're starting with a basics and getting some details on the design, construction, and characteristics of MLCCs. And it'll be one of our illustrious FAEs, Duong, that will take us through that this time. So without further ado, I introduce you to Duong, and she'll be talking to us about some of the details of MLCCs. So as you wish.
Thanks, Wilmer. Hi, everyone. So today, as Wilmer said, we'll be getting into the details of MLCCs. A bit about myself. My name is Tu. I attended Cal Poly SLO from 2015 to 2019, and I graduated with an undergraduate degree in electrical engineering. Now I'm with KEMET's FAE team, helping customers design in leading edge solutions to help them be successful in the marketplace. That being said, I am still learning a lot. So let's jump right into it. For today's agenda, we'll be covering what is a capacitor, MLCC designs, MLCC characteristics, as well as common failure modes. So what is a capacitor? Here at KEMET, we offer a variety of fixed capacitors, including film, ceramic, motor start, electrolytic, and supercapacitors. Today, we're going to mainly focus on multi-layer ceramic capacitors, or MLCCs. Okay, so what is a capacitor? A capacitor is a two-terminal electronic component that stores electrical energy in the form of an electric field. In this illustration, we can see a simple single-layer capacitor with two conductive electrodes, which is the gray material, separated by an insulative dielectric, which is the yellow material. Capacitance is the measurement of a capacitor's ability to store charge and is determined by the capacitance equation here. The unit of measurement for capacitance is farads and is calculated by the amount of charge over the voltage. If you have more capacitance, it means that you can hold more charge on the capacitor at the same voltage. To better understand that equation and how charge is stored in a capacitor, this water bucket analogy explains it pretty well. So the area of the bucket represents the capacitance, while the depth of the water represents the voltage. The volume of the water represents the total charge stored. So we can see for the bucket on the left, which is of a class 2 X7R dielectric, the area is much larger, which means it can hold more water at the same depth as the bucket on the right, which is of a class 1 C0G dielectric. That means that it has higher capacitance capabilities at the rated voltage. And when we look at capacitors, higher capacitance means that a capacitor can hold more charge at the same voltage compared to a capacitor with lower capacitance. Now, this analogy is not just for ceramic capacitors, but encompasses all capacitors. Ceramic capacitors come in a variety of dielectrics, form factors, and sizes, which are all driven by key application characteristics such as capacitance, voltage, temperature, mechanical, and reliability requirements. Now, let's get into basic MLCC design. MLCCs are constructed using alternating layers of ceramic dielectric with metal electrodes, which you can see in this illustration here. And each layer represents a single capacitor, and adding additional layers will add more capacitance as the MLCC are in parallel. We calculate the capacitance using the capacitance equation here, which you've seen previously. And by looking at these parameters, if we increase the dielectric constant, the area of the electrodes, or the number of layers, we'll see an increase in capacitance. We can also choose to reduce the dielectric thickness, since the capacitance is inversely proportional to the thickness. So if you were to reduce the ceramic thickness, say, by in half, that would double your capacitance. And because reducing your ceramic thickness in half, you can now add twice as many layers, which again doubles your capacitance. So the net effect of reducing thickness by half would yield a 4-fold increase in capacitance. This shows, in the slide, which shows an exploded view of an MLCC, you can see the construction of the entire component, as well as the dielectric and electrode layers mentioned in the previous slide. The yellow material being the ceramic dielectric material, along with the darker internal electrodes material. The MLCCs can be made using 2 different electrode systems, PME, which is precious metal electrode, or BME, which is base metal electrode. Now, historically, MLCCs were made from PME materials, in which their electrodes were made from silver palladium. And over time, as dielectrics became thinner and costs needed to be reduced, suppliers switched over to BME materials, in which the electrodes are made from either nickel or copper. Now, the difference between BME and PME is important. The layers are able to be made thinner using BME materials, and because of this, we're able to fit more of those thin layers in a component of the same size compared to PME materials, thus giving us higher capacitance capabilities. This made BME parts extremely volumetrically efficient and reduces cost. Now that we've just gone over the 2 different types of electrode systems, this slide shows which systems are offered across the different dielectric materials as seen here. Most commercial and automotive grade parts utilize the BME system, whereas older parts such as military and high reliability graded parts utilize the PME system. MLCCs come in a variety of dielectrics, and we categorize these dielectrics into 3 classes, which refer to their capacitance stability over temperature. Within each of these classes, we designate each dielectric using a 3-character system, such as C0G or U2J, which we'll get into in a bit. All right, so let's get into the ceramic characteristics. All ceramic capacitors will have some shift of capacitance over the operating temperature range. This graph shows the trade-off of the dielectric constant versus temperature. The formula we saw before states that the capacitance is proportional to the dielectric constant, so any changes to the dielectric constant will result in a change to the capacitance. Class 1 dielectrics such as C0G and U2J, their dielectric constants are relatively low, which results in lower capacitance values compared to class 2 and 3. Now, even though they have lower capacitance values, they are very stable over temperature compared to class 2 and 3. For class 2 dielectrics such as X7R or X5R, these dielectrics will have a higher dielectric constant compared to class 1, which will result in higher capacitance values compared to class 1. Now, although they have higher capacitance capabilities, they are going to be less stable over the temperature range. And class 3 dielectrics such as Z5U and Y5V, they will have a much higher dielectric constant, but they're going to be even less stable compared to class 2 dielectrics, and especially more so less stable compared to class 1 dielectrics. Now let's get into the nomenclature of these dielectrics and what they represent. So as mentioned before, dielectrics are classified by a 3-character system, which defines its temperature coefficient of capacitance. Class 1 dielectrics have a temperature range of -55 degrees C to 125 degrees C, and the 3 characters define how much that capacitance can shift over that temperature range. Since class 1 capacitors are considered very stable, their capacitance change is given in parts per million, or ppm, and not percentage. The first character will define the significant figure of temperature coefficient. The second character will define the multiplier of that significant figure. And the third character will define the tolerance of the temperature coefficient. So for example, for C0G, you would multiply 0 with 0 times -1, which will give you 0, plus or minus 30 parts per million per degree C, which will give you 0.3% at 125 degrees C. For U2J, you would multiply 7.5 and minus 100, which will give you negative 750, plus or minus 120 parts per million per degree C, which will give you 7.5% at 125 degrees C. Class 2 and 3 are specified differently because class 2 and 3 dielectrics are not as stable as class 1. Their capacitance change is given in percentage and not parts per million. The first character defines the minimum temperature range, the second character defines the maximum temperature range, and the third character will define the maximum capacitance change over that entire temperature range. So for example, a class 2 X7R will have a minimum temperature of -55 degrees C and a maximum temperature of 125 degrees C, and will have a maximum capacitance change over the temperature range of plus or minus 15%. For a class 3 Z5U will have a minimum temperature of 10 degrees C, a maximum temperature of 85 degrees C, and the maximum capacitance change over temperature range that it'll see is 22% to negative 56%. So as mentioned before, all ceramic capacitors will have some shift of capacitance over the temperature range. A design consideration is capacitance shift on class 2 and 3. On class 2 and 3 dielectrics when DC voltage is applied. This is called voltage coefficient of capacitance, or VCC. This graph shows the capacitance change for an X7R 1206 10 microfarad 16 volt capacitor from 0 volts to 16 volts. As you can see, as the DC voltage increases, the actual capacitance will decrease. The amount that the capacitance will drop will depend on the dielectric material, the design, and applied voltage. And higher voltages mean higher electric fields on the MLCC layers, which increases this effect. This slide compares capacitors with the same specifications except their different case sizes, one being 0805 and the other being 1210. So they're the same, the same capacitance and voltage rating, just different case size. You can see that the capacitance for the 0805 case size decreases much more than the 1210 case size. The reason for this is because the larger case size parts for the same capacitance and rated voltage will actually use higher voltage designs and therefore thicker layers. In this example, the 1210 part is using a 25 volt design. So when downsizing, designers should consider this effect. So why exactly does this occur? Class 2 dielectrics are made from a barium titanate material. Its crystal structure, which contains barium atoms at the corners, oxygen atoms at the face centers, and a titanium ion at the very center. Above 130 degrees C, which is what's called the Curie point, the crystal structure becomes cubic. As it cools down below Curie point, the titanium ion will shift within the crystal structure and take on a tetragonal shape. There will be a positive charge here and a negative charge here, which forms a dipole. A dipole is just a positive and negative charge separated by some distance. Each dipole has its own electric field going from the positive side to the negative side. Now, we'll see how these dipoles play a role when a DC or AC bias is applied in a bit. When barium titanate goes below the Curie point, or 130 degrees C, the dipoles will align to create domain regions, as you can see here. And these regions will be randomly scattered in all different directions with the dielectric material. The overall net effect is a cancellation of all the dipoles within the material. The process by which barium titanate creates dipoles, and those dipoles being randomly scattered throughout the dielectric, is called spontaneous polarization. So now, when we apply an electric field on the material, the titanium ion will shift within the crystal structure and rotate the dipole to align with the electric field. the ability of barium titanate to create dipoles. And the ability of these dipoles to rotate with the electric field is what gives the material its high permittivity. We call this material ferroelectric. When we apply an AC voltage to the capacitor with no DC voltage, the dipoles will be able to rotate and move with the changing electric field. We measure the capacitance using AC voltage, and the easier it is for the dipoles to rotate and align with the electric field, the higher the capacitance. If we now apply DC bias to the part, the dipoles become locked into place and are not as free to rotate. So when we apply an AC bias, the dipoles remain locked and reduces the overall permittivity of the dielectric. So that reduces capacitance. From that, comparing class 2 and 1 dielectrics, class 2 dielectrics are made from barium titanate, which is a ferroelectric material. So the dipoles will rotate within their domain regions with the AC field. And as mentioned before, the domains are going to be locked, the dipoles are going to be locked into place, and they're not going to be as free to rotate and move. And because they're locked into place, but they're still trying to rotate within their domain regions, that friction will cause domain wall heating and signal distortion. This is represented in the hysteresis on the left. On the other hand, class 1 dielectrics are made from calcium zirconate, which is a paraelectric material. The dipoles are not restricted by domain regions like class 2, so they're going to be able to freely move and rotate to align with the AC field. This means that class 1 dielectrics will not experience domain wall heating, and because there is no domain wall heating, you can expect lower losses compared to class 2 dielectrics. The key takeaway is that class 1 materials are much better for AC applications because it experiences lower losses due to no domain wall heating. So, all right, capacitance stability with voltage is not just applicable for DC voltages, but AC voltages as well. This plot shows an actual capacitance measurement of an X7R 1206 10 microfarad MLCC. The capacitance shifts from -8% at 100 millivolts to +8% at 2.5 V RMS. When we list the capacitor's capacitance in the datasheet, we measure it at 1 kilohertz, rated at 1 V RMS as the reference voltage. All capacitance measurements should be performed at the frequencies and voltages listed in their datasheet. This is important because you may take a measurement and see that the capacitor is out of spec. For example, here we can see an actual capacitance measurement of a class 2 X7R 1210 10 microfarad with 10% tolerance MLCC using an LCR meter. The capacitance is measuring out of spec, even though the instrument is calibrated, and the AC voltage is set to 1 V RMS, and the frequency is set to 1 kilohertz. So why exactly is this happening? Here, you can see that the actual voltage that is being applied to the capacitor is not actually 1 volt, but it reads 186 millivolts. Knowing that class 2 capacitors will have a shift in capacitance with AC voltage, it appears that the instrument voltage is causing the part to read incorrectly. So why does this happen? All capacitance meters have some source impedance, or ZS, ranging from 20 to 100 ohms. Capacitors will also have an impedance, which we'll call Z cap. As capacitance increases, the impedance of the capacitor will decrease. If the capacitor's impedance starts to get close to the impedance of the meter, there will be a voltage drop across the capacitor you're trying to test. The plot on the right shows that as the capacitance of the MLCC increases, the voltage that's actually being applied will decrease, causing a measurement that is out of specification. This starts to become an issue when measuring class 2 capacitors above 1 microfarad. In order to avoid that issue, it's important to select a meter that can compensate for the voltage drop due to the high capacitance part type. Some meters come with an auto leveling control, or ALC function, which compensates for the measurement by increasing the source voltage until the desired voltage is reached on the capacitor. And not only is it important to select an a meter with an ALC function, but it's also important to select one that has the ability to output over 6 VRMS to overcome the source impedance. Now, after going through that, you'll see a much more accurate measurement. Some newer LCR meters will have this ALC feature built in, so you won't have to go and manually do it yourself. So now moving on, it's important to note that class 1 MLCCs are ultra stable over both DC and AC voltages, as there's no change in capacitance, which can be seen in these two graphs. This means that class 1 dielectrics are stable over both voltage and temperature. Now let's talk about aging. Aging is the process in which capacitance changes over time, and it occurs in class 2 and 3 dielectrics. When capacitors cool down below Curie point, which is about 130 degrees C, the dipoles will align within the domain regions and be scattered throughout the dielectric. The domain regions within the dielectric will begin to relax and cause a slight reduction in the dielectric constant over time, thus lowering capacitance. The effect is a measurable capacitance drop between 1 to 5% per decade hour. Now, aging can always be reversed by exposing the capacitor above the Curie point. This process is called de-aging. And de-aging can always be reset back to its original start time. So when exactly do we measure capacitance? Manufacturers publish referee times on datasheets, which are the number of hours after the last heat when the capacitance is measured against the specification. For KEMET, most X7Rs will have a referee time of 1,000 hours, with some higher capacitance X7Rs having a referee time of 48 hours. Now, each KEMET specification sheet indicates the referee time for the part in question. KEMET's website also includes an aging rate calculator for designers to predict how much capacitance will remain after so many hours. And from this graph, we can see that class 1 dielectrics are not affected by aging and do not experience degradation over time. So not only are class 1 dielectrics stable over voltage and temperature, but also over the entire lifetime of the capacitor due to the aging phenomenon. Now, as mentioned previously, when an electric field is applied to barium titanate, which is a ferroelectric material, the titanium ion in the middle will shift within the crystal structure and become tetragonal. And when this happens, the structure will go through a mechanical distortion. So as the ion is moving with the voltage, the geometry of the part changes. This effect is called piezoelectricity and electrostriction. This is important in applications that are sensitive to electric or audible noise. When using a class 2 or 3 ceramic capacitor in an application with vibration, the mechanical forces are transferred to the MLCC through the solder joints and may generate an electric noise in the circuit. This is especially important near the input of amplifiers, where that generated noise can be amplified and affect the operation of downstream components. The inverse is also true. So for example, when applying an AC voltage in the audible frequency range to a class 2 capacitor, the capacitor will have some mechanical distortion which will couple through the solder joints and vibrate the circuit board. The effect of this is an audible noise at the same frequency as the AC voltage. Solutions to mitigate this effect is KEMET's KPS product line, which includes lead frames that isolates the MLCC from the circuit board to dampen the sound. Switching to a class 1 dielectric capacitor would also completely eliminate this issue. Now, finally, let's get into the common failure modes. Ceramic materials are used in many applications, including electronics. Some key properties of ceramics are that they have a very high chemical bond strength and a high elastic modulus. A high elastic modulus means that the material will resist deforming elastically when a stress is applied to it. This results in low ductility and a material that is very hard. Because of this, ceramics are inherently brittle and prone to cracking under excessive stress. But what causes a ceramic material to break? So there are 3 main sources of cracking for MLCCs, and each has a distinct crack signature. The first one being mechanical damage upon impact due to aggressive pick and place or physical mishandling. The second being thermal shock, which will create a parallel plate crack, which you can see here, due to extreme temperature cycling and hand soldering. The last one being flex or bend stress, which occurs after the part is already mounted to the board and will be more common for larger chips. And failures will not always be immediate, and we'll get into why in a bit. All right, so there are multiple types of mechanical forces that can be applied to any material. When we look at compression and tension on ceramics, the strength of the material is highly dependent on the type of force being applied. In fact, ceramic materials can have 10 times more strength under compressive loads as compared to tensile loads. This is partly due to the brittle nature of ceramics. So when subjected to tensile loads, ceramic are unable to yield and relieve those stresses. Also, any internal defects and flaws in the ceramic can cause cracks to propagate under tension, but not compression. So the key takeaway here is to remember that ceramic are strong under compression and weak under tension. In this slide, we can see a finite element analysis simulation of the capacitor under tension due to a convex PCB bend. As you can see, the highest concentration of stress on the capacitor is where the termination crown ends on the ceramic and meets the landing pad. Because of the high concentration of force in this region, this is the most likely area where a flex crack will form. All right, so as mentioned before, flex cracking occurs after the part is mounted to the board, and it's pretty common for larger chips. Flex cracking can happen when a PCB bends and causes a convex surface under the MLCC. And the area most likely to flex crack are where the termination crown ends and meets the landing pad, which will create stress from pulling outwards. Thus, MLCCs can never be shipped to a customer with a flex crack. It only happens after customer assembly. And flex cracking will always crack at an angle of 45 degrees, which you can see here, from the end of the termination crown to the other end termination. This will cut through the active layer of opposing electrodes. Now, the part will not always fail immediately. Flex cracks may go unnoticed until moisture and contamination enters the MLCC through the crack and create a fail short between the opposing electrodes. So to mitigate this problem, the first solution is level 1 protection or basic level of crack protection. This involves using a floating electrode or open mode design. In the floating electrode design, the electrode layers are in a serial configuration, and if the capacitor does crack, even if the crack breaches the active layer, the capacitor will still fail open and prevent a short circuit. In the open mode design, the electrodes are designed to be further away from the end terminations, and if the capacitor does crack, the crack will propagate to the termination and avoid the active layers of the capacitor, which will fail open and prevent a short circuit. Now, these are both great solutions for flex cracking, but the trade-off is that each one will have a reduced capacitance in the same volume. So that's something to keep in mind when choosing this solution. The next level of crack protection is level 2, which is immediate level of crack protection and happens to be the most popular method. In this solution, a flexible termination, which is made of a conductive silver epoxy and is added as an additional layer between the nickel barrier layer and the copper termination. Now, by adding this flexible termination material, mechanical stresses can be absorbed by the termination and reduce the overall stresses on the ceramic body. This improves the overall flex handling capability of the capacitor. In extreme cases of flex, this layer was also designed to tear away from the end termination to provide a safe failure mode instead of cracking the actual ceramic body. The main benefit with utilizing KEMET's flexible termination technology is that it does not impact the volumetric efficiency of the capacitor, as the internal construction of the capacitor is maintained, whether using a standard termination or flexible termination. The last level, being level 3, provides the highest form of crack protection for surface mount ceramic capacitors and is ideal for critical applications where short circuit failures cannot be tolerated. This technology utilizes a combination of KEMET's flexible termination system along with a floating electrode design or an open mode design. By creating this hybrid design, these capacitors have an increased flex capability, as well as a fail open design in case the capacitor does crack. All right. The second type of crack is due to thermal shock. The thermal shock is described as a rapid change in temperature, and when subjected to an MLCC, can lead to cracking. So ceramic capacitors are made from multiple materials and layers, such as ceramics, electrodes, and multiple termination layers. And then once they're mounted to PCBs, that'll add in additional material and layers. Each material has its own coefficient of thermal expansion, or CTE. When the capacitor and PCB is subjected to rapid changes in temperature, these CTE mismatches can cause thermal shock cracks, which usually looks like a horizontal line along the electrodes. Therefore, it's important to limit large temperature gradients in the capacitor and circuit board to avoid cracking. There are two areas where ceramics are most prone to thermal shock cracks. The first is due to hand soldering using a soldering iron. During this process, a soldering iron is placed in contact with the solder pad until reflow occurs. This usually creates a large temperature gradient, which you can see here, within the capacitor, and uneven expansion and contraction. To limit exposure to thermal shock cracks during this process, KEMET recommends not touching the capacitor termination during the soldering application. This will limit the sudden temperature rise in the capacitor. It's also recommended that the assembly is preheated to limit the max temperature rise to less than 120 degrees C during the hand soldering process. Now, keep in mind that large case sizes are more sensitive to hand soldering due to their larger thermal mass and are prone to larger temperature gradients. Another cause for thermal shock is the solder wave process, which also induces large temperature gradients on the circuit board assembly as well as MLCCs. To avoid possible cracking due to the solder wave process, KEMET provides a recommended solder wave profile, which includes preheat zone requirements within our data sheets. So we also recommend solder wave for case sizes less than 1210. With that concludes this presentation. So are there any questions?
Yeah, wait too. We actually do have a few questions, and thank you very much for going through all that. So we've got a couple of questions that came through, so let's get right to it. The first one is, do PME capacitors have higher reliability than BME in general when comparing apples to apples, so same voltage, cap size, and all that stuff?
I'm not too sure about that. However, in general, where you'll see PME used are in military and higher reliability graded parts, because those are older technology and like they're under DLA regulations. So it's a lot harder to adjust those requirements to use BME materials. Regarding if comparing the same exact capacitor specs, but PME versus BME, I'm not too sure about that, but I'll have to get back to you.
Yeah, that same question came up in a previous webinar, and generally it was like not especially. I mean, they happen to be used in those high rel applications, primarily, like you said, a lot of it having to do with historical reasons and other types of regulations. But really, the fact that you're using nickel versus palladium as your electrode, as far as I know, doesn't really have that big of an impact on reliability.
And I believe we do offer BME high reliability parts as well.
Right.
F32535s.
Right. So the next question is, are there any downsides or reasons to not exclusively use flexible terminations as in added lead time or cost?
That I'm not too familiar with, so I'll have to double check and get back to you as well.
Yeah, I do think we have most capacitor manufacturers for flexible terminations or soft terminations, whatever they're called, there is generally a premium to it. So while electrically the performance is all generally going to be the same, and it's tempting to throw in flex term whenever you can, because it is an added process, there is added material and all that stuff in the manufacturing process of these things. Yeah, there is a price premium to it compared to its non-flex term counterpart. Next question is there any acoustic effect on class 2 MLCCs depending on the DC bias? So I think you've got this one, class 2 and microphonics and all that.
Yes, so let me just go back to that slide. All right. So yes, so because of the ferroelectric material, yes, the answer is yes. So due to the DC bias, it will, sorry, can you repeat the question, please?
So it's just about DC voltage causing this acoustic effect. And I mean, and you're definitely right on the right path here, is particularly when coming from a switching regulator like a buck or a boost or something like that. It's supposed to be DC, but as we all know, it's got some AC ripple riding on top of it, and it's that AC that's causing this piezoelectric effect to be pronounced and cause resonance down to the PCB, and you get some audible vibrations to it. So it's definitely a phenomenon just of class 2 and 3s. Class 1s, because they're not piezoelectric, don't have that.
Mm-hmm.
All right, I'll take this next question way too. So the question is, can you provide a formula to calculate the remaining capacitance, as in from temperature, DC voltage, AC voltage? So we have our simulation tool, KSIM, that is capable of providing that information. So while we don't provide an explicit formula to get you that, we do provide a simulation tool that is capable of simulating that. We have a similar question. Can you provide a lifetime calculation for lifetime calculation formula? Wait, too, unless I'm mistaken, I don't know that we provide life formulas for MLCCs, right? We have our fit calculator, but that's not quite what they're getting at.
Yeah.
I know that we provide life formulas for our film and electrolytics, but it's not generally a consideration for MLCCs. Like, have you seen that?
Life calculator, I think usually customers will request for fit data and reliability data. Yeah. Yeah, but
yeah, it's not like in other capacitor technologies that that we do explicitly provide life calculation formulas and stuff. All right. Ooh, next one is a good one. Has KEMET tested their flexible termination system to flowers of sulfur testing in the past? And if not, do you believe they will pass the EIA testing? That is way out of my wheelhouse. I don't know that. Way too, yeah. Do you?
No, I do not.
So I'm sorry about that. We'll definitely have to get back to you on that. That's brand new.
It's an interesting question.
Yeah. Next one is, how can we find the max peak current allowed for a C0G capacitor?
For that, would that be something KSIM would be able to simulate, Wilmer?
Yeah, our KSIM tool that you can find on, if you go to ksim.kemet.com on any browser, if you pick your capacitor, enter your operating conditions, and you could switch to see the maximum allowable ripple current, and it's when you multiply that by ESR, you get your ripple voltage. So yes. I don't quite understand this next question. The capacitance D rating versus DC voltage is instantaneous? Question mark. Yes. So do you have a curve, cap versus voltage in that presentation? I forgot.
A curve, voltage versus, sorry, what?
Cap versus voltage. When you talk about VCC. Yeah. So the effect does happen instantaneously. For the first percentage up from rated voltage, as you can see in Huei-Tu's presentation, it actually goes up for a little bit and then starts to drop pretty far down as you get down through to your rated voltage. And once you hit your rated voltage, you can have as much as, what is that, almost 60%. So the effect does start to happen pretty immediately. And when people are designing in capacitors, there's several ways to sort of counteract this effect. You can either spec in more cap than you need, so that by the time you get to your rated voltage, you have the cap that you need, or you spec in more voltage, right? So you kind of push that curve, that point out to the right further and further. So those are two ways you can kind of get around that. Does class 2 aging also appear on its impedance above self-resonance? Huh. I would expect it to, right? Right, way too, right? Because as we know, self-resonance is the resonating effect between the sort of main capacitive body and all the inductive parts of it. So if that capacitance is sort of decreasing over time, I would expect the resonant point to move out, right? To move to the right a little bit. Your capacitance is decreasing. So, I mean, we can't really get around the physics with that. It is what it is. All right, we'll take, got a few questions we'll probably have to answer after the fact, but this next one is, are VCC and TCC additive? So do the effects compound each other? So if you don't mind, wait, I'll take this one because I think I've had some discussions with the ceramic team on it. And in general, you can consider the two effects to be additive. Now, they're not linear in the sense, or at least we're doing some studies right now to understand if they're linear in the sense that is it just additive across the board, right? Can you just stack the tolerances, if you will? And we're efforting that as we speak. There's some studies underway where you basically end up with this three-dimensionally equation where you have voltage, temperature as a parameter, and measuring that and compounding those effects can get kind of challenging in the lab, right? Because that implies that you have to put it into some sort of temperature chamber while at the same time applying a certain amount of bias voltage to it and measuring that. So it can get pretty challenging. It's probably a good sort of conservative approach to stack them on top of each other with some margin. But to be 100% precise, we're sort of efforting that as we speak, and we'll our simulation tool will reflect that in due course. So I think we're kind of over time right now, and I think that's all the time we have. So if we have a question we didn't get to it, I apologize. We'll reach out to you after the fact. And with that, I'd like to thank Wei-Tu for putting this together. So thank you for your time putting this together, and thank you everybody for attending. And join us in a couple of weeks' time when our next webinar will be all about ESD solutions. So thank you for joining us, and we'll see you at our next webinar.
Thanks, Wilmer. Thanks, everyone.